become you the second.
Okay.
So the second person was Julia. And
Yes, I'm here.
okay.
Good morning. Good afternoon.
Julia? Oh yeah, you were talking about that earthquake that occurred on July 4th or very recently.
Yeah, exactly.
Okay. Do you want to share
Okay.
your screen and
Yes, sure. Okay, this one. Okay,
looks good.
it's good. Okay, good. So, good morning, good afternoon, everyone. My name is Giulia Reggi. I'm a PhD student at University of Trieste, and today I will show you some results that I obtained by using GMTSAR. I have to say that I'm really interested in time series processing, but today I will show you only 2 interferograms because I'm still working on time series processing in Northeast Italy. I had some problems, but I solved them. So I hope that in few weeks I will obtain even some results with the time series. Well, anyway, as I said, today I will show you the results related to the earthquake that occurred in Iran at the very beginning of July. So it was a strong earthquake, magnitude 6, that hit the southern region of Iran with a depth, epicentral depth of about 10 kilometers. So it was a very good example to test GMTSAR. And also the area is new for me because I usually, as I said, I work in Italy. So I started with the ascending geometry. So I downloaded 2 acquisition just before and after the event. And as you can see on the right, I put also the screenshot of my configuration file. I modify something and I try some parameters. But here, okay, the results. For the ascending geometry, as you can see, the deformation can be observed in the subswat number 2 and the subswat number 3. And here I put the amplitude and the correlation plots. So the red circle on the right indicates the area interest by the earthquake and the ecoseismic displacement. So as you can see, especially in the correlation plot, the area is characterized by a really good correlation, high correlation. Okay, and also I reported the interferograms. So the wrapped phase just before and after the filtering step. And as you can see here, okay, sorry, on the right, the area of interest and all the fringes that indicate the surface displacement occur with respect to the satellite itself, so along the line of sight. And we can count here about 8, 10 fringes. So we can think about a displacement of about 30 centimeters, more or less. Here, after the merge script, the entire frame, and on the bottom panel represents the area of interest. After the filter step and also the application of the mask. And also the geocoded unwrapped phase of the same area. So the entire region and the area of interest. And at the end, I also plotted the results that I obtained, the geocoded map on Google Earth. In particular, here we can observe the displacement along a line of sight in ascending geometry. So here the area, the red area represents a range decrease of about, as I said, 30 centimeters. And also I report here the same map, but in radar coordinates. Yesterday, I presented this result to the other guys, the other colleagues of Team 6, and to David and Eric. And I also try with the descending geometry. So now I will show you the same maps, but in descending geometry, as I said. So again, here we have the amplitude and the correlation, in this case only for the subswapped number 2. And again, red circle, the area affected by the main event. So the phase, so on the left before the filtering step, and then after the filtering. And here the area, as you can see again, the number of fringes is again about 8 to 10 fringes. Here the entire region and only the area of interest, the geocoded wrapped phase and the unwrapped phase, again in radians. And after the geocoding step, here we are, the Google Earth product, the maps, which represents the coseismic displacement occurred in the area, in the southern Iran, with respect to line of sight, but in the descending view, geometry view. And again, we observe this area affected by displacement of about less than 30 centimeters in this case, where we can observe a range decrease. And okay, the final result in radar coordinates. And I think that's all. Thank you very much for your attention.
Great, thanks. More results since yesterday. That was great.
Yeah, I work during the night. Yeah,
it's great to see the descending one. It's really kind of, you see the same pattern, but you know, from a different view. So it's interesting.
Yeah, as you said yesterday, I think that there are still atmospheric effects again, even in the descending geometry. So this is my goal for the future, to remove the atmospheric effects with all the methods that you explain. So this is another future goal.
Yeah,
Any more
that's
questions,
great.
Julia? Yeah. That was great. And when you do the time series, you're going to have to do the atmospheric corrections, definitely.
Yeah, exactly. But I'm still working on that. I hope to obtain the results soon. So I'm looking for that.
Nice. Okay, well, we should move on. We have more talks, but that was great. So Diana, are you ready to present?
Yes, hi everyone. Sorry for before. So I tried to share my screen. Just tell me if you see it.
It's coming. Yeah, we see it.
Yeah, full screen.
Yes, perfect.
All right. So yes, I'm Diana Orlandi. I'm a PhD student at the University of Pisa, and I am glad to show you my little work with the GMTSAR that was about the land subsidence occurring in areas affected by fluid resources overexploitation. So actually, I dedicated the first slide to a little bit about me. So as I said, I started the PhD this January. So at the Department of Information Engineering, but my background is mainly geology. So I'm interested also apart from the processing, also the interpretation of the data. So that's why I also joined, and I was super glad to be accepted to join in the GMTSAR. And I'm glad to see that in 1 week I was able to learn a lot of stuff. So yes, basically, as I was saying, the area of interest is here is kind of Larderello. It's in the province of Pisa in Tuscany in Italy. So because this is the first, actually it's the first processing I just launched with the beginning of my PhD. It was with the SPAS approach with the platform that is the GeoHazard tech. And this is a time series analysis because it was 4 years covering 2017 and 2021 and with the Sentinel-1A data. And I did actually both orbits, but here I reported only one. But as you can see, there are interesting spots, especially, apart from the main cities affected by urban subsidence and water extraction. Here, I don't know if you can see my mouse, but here in this area, there are spots interesting affected by, actually there's a reservoir of geothermal field. So this area is very exploited from that point of view. And yeah, for me, it was actually interesting to study it with the GMT. So I have to say that I had a lot of problems, errors. During this week, I encountered all the errors that I could. So yeah, this is the DM that you all loaded and that I did with the GMT. Only I chose this short area. And this was my main big mistake because actually for the DM, I chose a shortened area. And then for the processing, actually, I chose the whole frame. So actually, yeah, for this processing, I chose 6 months that, well, no, 7 months that go from December last year and June this year. And these are the parameters and of the path and the frame, with a total of 39 interferograms. So the master I chose is, let's say, roughly March 2022, but it was the better one. And as I was encountering some errors during the creation of the interferograms in the two subspots that goes like I22 and I33, I only did the I11. So the point is that I was lucky because my AOI was covering, the F1 was covering that area. So what I got is an interferogram and also the wrapping. So here I reported the coherence, and as you can see, the areas where I'm actually interested are a little bit low coherence, but despite this, I was able to obtain a good result. Let's say that it's kind of what I was expecting, because with the last study I did with the other approach, I got like a rate of 1.5 centimeter per year. So that's pretty good. And this is the unwrapped phase. So what can I say? Let's say that I can have my conclusions, because I encountered many errors. I don't know if all of you did, but of course my big mistake was choosing a wrong them. So I tried from yesterday to choose another one, but I had some problem with the virtual machine, with the Google, and so I'm planning to do the next days. And actually, if we keep in touch, I would be glad to share. And yes, and of course, during my PhD, I'm looking forward to use it. So this is just the beginning, let's say. Thank you.
Great, thanks.
Thank you.
Nice results. Are there any questions? Diana? So why, I had one question, why, I didn't ask you before. Why are those areas so decorrelated? Is that a lot more vegetation there?
Yeah, yeah. And actually, I also saw in the descending with the other approach that it's kind of the signal is not that good, but I figured it out. Actually, my PhD is also involving machine learning. So with my team, we were thinking about some kind of approaches like for so with some regressions to kind of predict, but it's everything so at the beginning. So you can imagine I just started in January, so it's just everything to be still decided yet. So yeah.
I mean, the correlation's okay. You're getting a pretty good result. So yeah.
Yeah.
Let's see, any more questions? Nothing in
I'll
the
ask a question. Yeah, so that's really cool. Do you have any available well data to look at what the well record's doing as it relates to the deformation there?
Actually, I was what we were thinking about with the machine learning, yeah, to integrate and just to have more data to put it. But the thing is that for example, the piezometry, I don't know if it's in English, the piezometry level, it's right in the translation. But the point is that they are very sparse. So, you know, with INSAR, you have a certain coverage, but then these stations are like kilometers apart, very far from each other. So the well data was not that best. So we also thought about it. I was thinking to merge with some kind of data like soil moisture or other data sets, but yeah, the well data are not that many.
Yeah, because when you eventually have time series, it'll be really, really interesting to see how that deformation relates to them. So
yeah,
I know getting well data is always challenging.
Yeah, and actually in Italy, it's everything related to the region. So there are some regions that they do public data and you can just click on it and have it available. While other ones, you just have to have some requests, some permissions. So it's kind of, yeah. But thanks for the question. It's interesting.
great, thanks. So the third presentation is Ronaldo, and I could show it or Melissa could show it, but I can't remember how to tell Zoom to send. This is a video. How do I tell Zoom to, oh, you want to show it?
I could do it. I could do it.
Okay.
Yeah. Give me a second here.
Can never find this. There we go.
At the University of Luxembourg. I've been working on hydrogeodesy, and I'm very happy to be part of that GMTSAR workshop. In the following presentation, I will show you the result of using images for characterizing the co-seismic displacement caused by the last big earthquake in Haiti in August 2021. This earthquake was happening exactly on August 14, 2021 at 8:29 in the morning at the local time, with a magnitude 7.2. It was located at 125 kilometers west of the Haitian capital city, Port-au-Prince. And this earthquake had very huge impact on the country, with at least 2,200 dead, 12,200 injured, thousands of structures damaged or destroyed, and economic loss estimated to around $1.6 billion. Now, to conclude this study, I consider one pair of pre- and post-event ascending Sentinel-1A satellite images. The pre-image was accurate on August 5th, and the post-image was accurate on August 17th. And the earthquake was happened in between on August 14. On the right image, I show you the merged tree substrate footprint from the assembly track 4 that we use. For this study, I found two results. The first result is the interferogram. On the map on the left, we have the interferogram for the ascending geometry. The black star on the map represents the epicenter of the earthquake, and we have different contours also on that map. Each contour indicates the movement in the light of sight direction. We can see on the west part of the epicenter, we have more closely spaced contours, which indicate greater amount of deformation in the light of sight direction in that area. Also, I compare my result with the published paper before. We can see that the two interferograms are quite similar. Except in the case, you can see in the soft part or the north part, we have some small images. They are related to small islands in that area. This is what I see when I check on Google. The second result I have is the surface displacement for the ascending geometry in the light of sight direction. The different surface values contained in the previous interferogram is converted into displacement. And we can see on the west part of the epicenter an obvious red pattern, which indicate the surface displacement in the light of sight direction. And again, I compare my result with the same published paper. We can see that the two surface displacement are quite similar, except in my case, in the peak value is around 0.6, and in this case, he has around 0.5 for the peak value. After that, the two surface displacement are quite similar. And that's all. Special thanks to UNACO and all organizers.
That was great. It was too bad Ronaldo's not here. I guess we'll have to email questions to him. But it's also too bad he should contact Jawa, because Jawa and one of our students have been trying to unwrap the phase of that interferogram, and they know all the tricks. I don't know if you want to mention what the tricks are, Jawa. But,
yeah, so the major reason is because of the strong decorrelation at Haiti, and also the strong ground shaking from the surface rupture that made phase unwrapping really hard. If it's not taken care carefully, you wouldn't be able to produce the right amplitude, because every single time you're trying to jump from a lower phase to a higher phase, sometimes you would create a discontinuity there, and the final amplitude wouldn't be large enough. The algorithm is a little bit complicated. I don't know whether I want to go through that right now, but generally speaking, what we're doing is that we're trying to divide the data on each side of the fault and try to make it continuous, as continuous as possible on each side of the fault. That's what we did.
great, yeah. So those were the three students from Eric Lindsay's group. So I should thank Eric for coaching them and the nice presentations. So I think next is Catherine Gunn's group. We're trying to get the European students done first, but everyone's in a different time zone, so it's going to be difficult. But I think Catherine had three students. Is Rui Oliveira here?
Yeah, yes. Hello, everyone.
Morning, or afternoon, or evening.
Can you see the screen?
Yes.
Okay, nice. So my name is Rui Oliveira. I'm researcher in applied geophysics in University of Évora in Portugal. My work is about the GMTSAR data and processing of datasets from São Jorge Islands, from Azores in Portugal. In this site occurred seismic swarm crisis since March of this year that affecting three islands. I used two pairs of Sentinel-1 SLC data from March 15 and March 27 of this year with descending track. So in this location occurred lots of seismic events since March 19. The earthquakes was felt on land by the population. The population stays very scared. Occurred more than 700 events per hour, and the maximum magnitude felt was magnitude 4.0. The depths of epicenters are located between 7 and 12 kilometers depth. So we think this is a seismovolcanic event occurring in the area. In the site, several teams are studying the site. I'm from the team of University of February, and we and the Kml authority, we have a funded project to study with seismology, atmospheric measures, and INSAR this site. So, as I say, I started to learn about the INSAR processing since March of this year. I need to study more. And when I started with Snap software. I have some problems with overall the computer. The operations are mouse click operations. It's weird to process data with the mouse, and I had limitations of hardware and to apply operations with errors, and the program blocks lots of time. So after that, I searched in the internet about training about INSAR data, and I discovered the Navco and the software GMTSAR. So I'm here, so learning the software is lots of. It's very easy to use, and I'm very motivated to use it. It's a very versatile software, and we can, in my opinion, we can have full control of data and operations. In this learn process, I had some problems due to installation, incompatibility problems with some functions, but are solved right now. So I processed the data. So showing some preliminary results about this pair of image. The processing allowed to produce phase field the grid, and also the LOS and unwrap mask, and the correct and unwrap dataset. Sorry, we can see in the phase field some fringe in the islands that have more earthquakes. In the north part, I can count 2 fringe. So I think the deformation can the quantity of deformation is about 5.6 centimeters. But in this part of the island, the north part, is very cloudy. So I think this can maybe these are related with problems of corrections. So I would like to ask for opinions for this possible problem, and also for other problem, that is the vertical lines in the I have vertical lines in this part of the graphics, and I don't know what is this, and the color map change in this part, and maybe this is a problem that can be corrected, and I would like to ask for opinions about that. I applied also the GNSS correction using continuum GNSS stations that are located in these pink points. So the final maps show that the deformation in the island maybe have the quantity of 10 millimeters, I think, but I don't know. And here we can see the vertical line problems. In this part of the fringe are located the most of the earthquake occurred. We have some problems in this island, the South Island, with these cycles. I don't know if this is a problem in the results, but with the GNSS correction, the cycles disappear. And here are again the vertical lines in the data where the colors change. So I would like to ask for opinions. And that's all. Thank you very much.
Great, thanks. Looks like you had made some progress since yesterday too, but maybe I didn't.
Yeah.
So maybe people have ideas or comments about whether or not that could be an atmospheric signal or not, or I don't know if we discussed this yesterday. The vertical line color change is probably a phase unwrapping error, but that's not a really big deal. But what I saw is that this signal isn't really correlated that much with topography, whereas the one maybe in the center of your image there on the other island to the southwest, there's a big signal that might be topographic error.
Okay. In this part, the altitude is very high.
It's very light. There's not much change, or yeah.
And in this South Island, there is a change in the altitude between in the left part and the right part. I don't know.
That's probably a phase unwrapping error, and
Okay.
But yeah, I guess if you make more interferograms, you will know.
Okay.
Real.
Okay.
It's very nice. Yeah. Any other questions or comments? I was just looking at Google Earth, and if you zoom in to that northwestern island, around where that red thing is, there's a whole line of volcanoes that I guess they aren't active anymore, but it's definitely a big geologic boundary there. Something.
Okay.
All right.
So thank you.
Oh, that's great. Okay, so we have a couple more people in Catherine's group. Alicio, there were two presentations. I think they're both on rock glaciers. Is Alicio here?
Hello, can you hear me okay? My internet now is not working so well, so I'm not sure.
I can hear you, but will you be able to show your slides, or if you put them
I'll try.
You want to try showing your slides? Yeah, perfect.
It's okay, great.
Yeah, great.
I haven't done much since yesterday, so I will show the same more or less. This is my study area. This is a sector of the Andes in northwestern Argentina. I'm a PhD student from Argentina, and I'm studying rock glaciers in different locations in the Andes. For those who don't know what is a rock glacier, it's a periglacial landform that it's composed of rock debris and ice. You don't see the ice in the surface of the rock glacier, but there is an ice core below the rocks. So this landform is moving very slowly downslope with a speed of centimeters or meters per year. And it's a very common landform in the Andes, in the dry arid mountains. I did a very basic processing. I only used 2 images with a temporal baseline of 24 days and 5 meters of perpendicular baseline. And I will show you the results. These are the results in SAR geometry. As the rock glaciers are very small, I changed to geometry to normal coordinates to detect the rock glaciers. I focus my my work in the southern part of this image. I did the unwrapping, but by now I only want to know if the rock glaciers are moving. I don't care how much now, at least. In the future, I will try to improve the processing and try to know how much they are moving. And also I have a lot of problem because this is an area with very high mountains, at least 6,000 meters. So I have a lot of atmospheric effect. And also I think some clouds in the image that generate some errors. So I only look for rock glaciers using the rapid phase, and I detect some of them. I have some results only in very big rock glaciers because most of them are very small. So I don't know if the resolution couldn't be, it wasn't enough to detect them. I have to try. Yesterday, David told me that I have to try using another value for filtering. I haven't had time. So these are the results. I can see that these rock glaciers, at least, they are moving. And that's a very important factor because if they are moving, they have a lot of ice, and that it's very important to characterize them for my work, at least. So this is some of the rock glaciers that show a phase shift that I interpreted as they are having some deformation in this short period of time. And that's all. It's everything.
Thanks. That was great.
Thank you.
It's something brand new for me. I saw it yesterday, but it's really interesting. I don't know if people have questions.
Yes, I have a question.
Yes.
So I didn't understand. Did you detect horizontal displacement or is it vertical displacement?
No, none of them. This what I'm showing here is not displacement. It's just the rapid phase. And I understand that it's looking in the line of sight of the radar. So I'm measuring only a component of the horizontal and vertical displacement. I understand that to measure the horizontal or the vertical, I have to use ascendant and descendant image, and then discompose the vector, and I have to know the slope of the terrain. And with that data, I can know how much in the horizontal or vertical they are moving. But so far, I only want to measure in the line of sight of the radar, only to know if there is any deformation in the surface.
Yeah, could you please remind the velocity of the sliding?
Sorry?
Could you please remind the velocity? You said it's 1 meter per year?
Yes. I have also measured these landforms in the terrain using a GPS, and they move, in the case that I measure, 10 centimeters 15 centimeters per year. In some cases, they move more, a meter per year. So I believe that only in 25 days, the movement should be only a few millimeters or centimeters, no more than that, only in 24 days.
And for this like kind of testing, you which time period you used between the images?
The time between
Yes.
images, 24
Yes.
days.
20.
Yes, I
24
want to
days?
try with shorter and longer time baselines.
Oh, I see. Okay, awesome. Thank you very much.
Thank you.
So to follow up on his question, when you did the GPS measurements of was that mainly horizontal or vertical, or when you went in the field?
When I measure with the GPS,
Yeah.
I went. I measured during a year. I went one time, measure point, and then came back the next year and measure again. And I have the vertical and the horizontal displacement. And as they have ice, the vertical displacement is also because of the ablation of the ice core. So they move in the horizontal as they move downslope, and they also move vertical because of the downslope and the ablation of the ice core.
Yeah.
And I put points in the surface of the rock glacier, and I go every year and measure those points again.
That sounds great. I'd love to join that field trip. Yeah.
Wherever you want, whenever you want.
Okay. Okay, I see some discussion in the chat, but it's more on unwrapping phase and closure errors. So we can talk about that later on, but that's another great topic. Okay, so next up is Veronica. And she, as I remember, she's working in the same part of the world. So get away, Veronica.
Yes, we work together with the Liceo. So I'm going to share my screen. Can you see my screen?
Yes.
Perfect. Okay. In my case, I'm also working in the northwest of Argentina, in the Cordillera Oriental. But in my case, I am working with time series, and I want to detect also the movement of the rock glaciers if I can. And I know that there are a lot of landslides in this area, so I want to detect them because there are no inventory of them in the area. So this is part of my master thesis. And currently I am doing an internship in the GNR IREA in Naples. So I am also using GMTSAR and another software which is from the institute in which I am working on. In my case, I am going to show you the results of the ascending orbit, but I work with both ascending and descending. These are the results. I used Sentinel-1B from 2020 to 2021. The acquisitions were every 12 days. In total, I downloaded 62 images, but as the area was too big, I have to merge 2 images, which were acquired in the same day. And also a big earthquake occurred in November 2020. And one of some interesting thing to do is to detect if I can measure how much the formation was related with this earthquake using the time series. This is the folder structure that I use. In my case, the area in which I am interested is only in the subset 3. So I didn't work with F1 and F2. And I follow the steps of the manual. This is the Argentina. I am working in this province right here, which is mainly in the limit between Jujuy and Salta. I use these 2 points to limit the study area, and I am interested in working in this red area right here, so that's why I only use one subswat. And these are the path and frames of the images that I downloaded from the Alaska search facility. And I use them the SRTM1. Okay, I download, this is mainly about the processing. I download the orbit files. I had some issues with this at the beginning, but then I could fix it, fortunately. So I think the processing more or less was okay. I selected an image of August 2020 as master, and I aligned all the images with respect to this one. This is the red of interference of acquisitions that I selected, and here is located more or less the image that I selected as master. For doing the interference, I choose a temporal baseline of 120 days and a perpendicular baseline of 100 meters. And I generated 203 interference. This is the network that I use. I was playing a little here, and I changed, for example, some parameters that for example, you recommend the range decimation and azimuth decimation as 8 and 2. And as I want lighter images, I changed this to 20 and 5. But yesterday, the professor told me that I also should change the filter wavelength. I didn't have time to do it, so these are the same results. So the filter wavelength in this case is 200. For the unwrapping of the interference, I selected a coherent mask because the area is highly vegetated in this black part here. This is I'm sorry, the neighbors are screaming. This is the stack of the coherence. As you can see in this black part, a lot of vegetation. So I selected a very high mask, coherent mask to unwrap, to avoid some unwrapping errors. So I selected 0.4 as threshold, but I did this before doing the course, so I didn't know that I should change this value here also to 0.4. So maybe I don't know if this is okay. Okay, these are the results. As you can see, it has a lot of relation with the topography, because these results are, in this case, the atmospheric correction is not implemented. I am implementing, I'm running this again, but it's taking some time, so it didn't finish yet. As you can see, okay, you can see nothing here. It's the truth. The earthquake occurred in this area here, but if you zoom in, you can see some rock glaciers and some landslide, which is what I am looking for. For example, this is a landslide, really small, because these are a little more than 3 kilometers. And as you can see here, maybe it seems that is moving towards the sensor. So I assume that I have no information here because it moves fast that I can detect with my network. I assume, I don't know, maybe you can tell me, because in a lot of, in the final map, you can see that you have some, for example, like these different color areas, but in the middle there is nothing. So, and if you see the mask, for example, the direction of the satellite, I should have information in this part. And I assume that it's a problem of or coherence maybe, or that's why it's moving faster that I can detect. And here you can see some rock glaciers. These are from the National Inventory of Rock Glaciers, in Argentina. And I can see a color here. I assume, I hope this is not related with the topography. And I can detect some of them. I cannot measure how much they are moving and also the landslides, because first I need to fix this atmospheric problem that I have, because if not, I don't know if I am really measuring, okay, how much they are moving, or if I also measuring some problems or some fake measurements that are related with the atmosphere. So first I need to fix that, because I did many tests for this area, and in general my results were not so good, mainly because all of them look like this, and I don't know how. I assume that if I use the here also the reference point is also already set, so it's not that problem. So maybe if you have some suggestions that I can use for improve my results, they are welcome.
Great, thanks. Those are nice preliminary results, yeah. Any questions or comments? It's a pretty big data set, so it's hard to work with.
Yes, it is a really big data set, and I also did the same, but with the entire time series. I am not showing you those results here, but I did the SBAS with all the available data. So, and I also did this with the ascending, and then I want to transform the ascending and the descending to the displacement in the horizontal, in the east-west, and in the vertical. But before to do that, I need to see that my results are okay. If not, I think
Well, you have the time series expert. Catherine is there to help you. You don't want to send her.
she's helping me.
We've been working.
The problem with these things,
and we will continue working.
Data set is so large that you make one change and then it takes a few days, maybe a week, to see the results, and it's a very slow process, but looks very promising.
Still running.
Oh yeah. What takes the longest of all the processing? What would you say is the longest?
In my case, the aligning.
The aligning.
It takes forever.
Same.
Yes,
that's what I would say as well. Yeah.
In my case, the SBAS, it depends. Now I am running the SBAS with the atmospheric correction, so it takes more time. But if you run the SBAS without any extra parameters, it is really fast. And also doing the interference and the unwrapping, for me, is not so slow, but the aligning, okay, you'll leave the computer there and then you return to the next day, more or less.
Yeah.
You got to keep those computers busy because they sit most of the time, they do nothing. So
right.
More questions? That was great. All right, so that was Catherine's group. Thank you, Catherine, for coaching. Interesting results. So I guess we're going to move to Matt Way's group here, and we have two presentations. There might even be more. If someone wants to do a presentation today, just put it in the chat and we can arrange it. If you want to show good results or bad results or things that didn't work, anything is fine. So we need the feedback on how to prepare the documentation and fix the software and that kind of thing. So yeah. Okay, so Lynn Lee is going to present, and I see you there. So if you want to share your screen.
Okay, sure. Okay, so hi, I'm Jack, and I'm from Taiwan, and I processed one earthquake event in Iran that's in 2021, and so next. Okay, so I'm not really familiar with the tectonic settings around there, but I assume this map shows the major structures that are like northwest trending and dip into the northeast like this. And this red rectangle is where the earthquake took place. And if you zoom in, it's here. And the magnitude is around 5.8, and the date is April 18th, and the depth is around 8 kilometers. It's pretty shallow, and the magnitude is pretty moderate. So I process, okay. And if we zoom in a little bit more, you can see here we have an anticline here. And yeah, and in the map, things around here. So basically, I think this earthquake just happened beneath that anticline. And if we see this focal mechanism, it should be a fault plane that is dipping to the northeast, and it's a low dip fault plane. It's around like 20 or 30 degrees. So I processed two pairs of Sentinel-1 images, and the left one is the ascending and the right one is the descending. So this is the fringes look like. And when I process this and I look at this, I think there's not much decorrelation happening there. And I think the fault didn't rupture to the surface. Okay, so I unwrap this and I get the line of sight displacements. But okay, and next I did is I assume there's no north-south direction. Okay, I assume there's zero, because since we only have two data for the inversion, so I can only solve for two unknowns sufficiently. So I did a 2D decomposition. So, and this is my result. So if you look at the vertical part, it's pretty straightforward that this is an anticline and there was an earthquake. So on the anticline, it experienced some of the uplifts. So it's around like 20 centimeters, and here a little bit of subsidence. And to the east and west, this part is moving to the east, and this part is moving to the west. So, and I plot them together, and I can make a map like this. So this part is moving to the west, this part is moving to the east, and the colors represent the vertical motion. And there is one literature that is investigating on this earthquake, and it has a simple inversion fault slip model, and the fault slip is inferred as a buried fault like this, buried beneath 1 or 2 kilometers, and it's like this, deep into the northeast. So based on these observations, I think I came up with an easy model that the fault is somewhere here, and maybe here we originally had an anticline, an analog of it, and the surface here. So when the fault ruptured, it caused uplift here and all the way, and all of the anticline as well. Just everything just moved up. But on the two sides, one is moving here, one's moving there. Like it's a little bit like inflation or just expanded. So what we see here is we see uplift and the horizontal movements as well. So I don't know if I'm making any sense of this, but this is the model and the interpretation that I can think of. And thank you guys.
Thanks. Wow, you got into the modeling already. That's good.
Just a really simple analog.
It makes sense to me. Any questions or? It's really a beautiful signal. There's no decorrelation there, it looks like.
Yeah.
Nice. And you've just processed those two. You could probably do other pairs that span the event, but you probably won't see any. I don't even see any atmospheric artifacts in your data. So
yeah.
Pretty lucky. Yeah.
I have a question.
Yeah.
So looking at the focal mechanism, it seems like there should be some north-south motion. So I'm wondering if that assumption you made is, if that's not correct, then what would be the result in your maps? Like, how are they going to be kind of biased by that assumption?
Yeah.
And
So
I wondered if you could, yeah.
So basically that assumption is because line of sight displacement, that vector is not sensitive to north-south displacement. So I'm making that assumption. But I think if I can recover the north-south displacement, I think this part and this part will go like a little bit like northwest and southeast, like it's going the ellipsoid, the shape, like it's going along that anticline ridge. I'm thinking that way, but now I only have these two directions, so I cannot really solve for that north-south displacement.
Yeah, I guess we're waiting for NISARs, then we'll have the four different look directions, and we can get the true 3D.
Yeah, exactly. Thank you.
Or you could subtract your model from the data and see what, how well it fits and how much north. Yeah, this is great.
Yeah.
It's very shallow earthquake. It's only a 5 point something, you said?
5.8.
Yeah, and it's really shallow, so you get a big signal. Wow.
Yeah.
Nice, thanks.
Thank you.
Okay, so we have another presentation from Matt's group, Yaki Song. I don't know if Yaki's here. Here, hi.
一起 may I share my screen?
You should be able to share your screen, yes.
Okay. Oh, can you see this?
That looks good.
Okay. So hello everyone. I'm Yuqi Song. I just finished my undergraduate study last month, and I'm going to start my PhD program at Peking University this fall. It's happy to be here and share my GMTSAR course project. It's about interferogram processing and damage profiles mapping. The case is for the Lushan earthquake occurred last month. So the study area around Lushan County is in Sichuan province in China. It's in the southwest part of China and where the topography is very complex. In some parts, you can see the elevation can be up to 4,000 to 5,000 meters, and many faults distribute here. Many earthquakes occurred here, like the Wenchuan earthquake occurred in 2008, and in Lushan County, in recent years, there are 2 earthquakes, respectively in 20 and 30, and the earthquake this year. So here, okay, here I choose this year, this earthquake occurred on June 1st. So to look into this earthquake, I choose the Sentinel-1 image on May 17th and May 29th, which are before the earthquake, and also the images acquired on June 10th, which is after the earthquake. I made 2 interferograms from the 3 images, but unfortunately, we can see that in some parts, the interferogram don't look very well, especially in the region around the epicenter. And it may be caused by the mountainous terrain and vegetation cover, as well as some other factors like water vapor. So then I check the coherence relationship map of the 2 pairs. You can see that in the city region, the pixels are much lighter, so which means the coherence is good. While in the mountainous region, they look very dark, so the coherence is coherence is poor here. So that's why we can't get a very good interferogram here. But after I got the coherence map, I can produce the damage proxy map. Damage proxy map are used as guide to identify damaged areas after the hazard. It is produced by calculating the difference between the coherence map before and after the disaster. And before okay, let's say those red dots show the place where the coherence decreased the most after the earthquake, which means they may be damaged to some extent after this hazard. And later, I plan to look into those high damage proxy area. In the mountainous region, the coherence change can show the probability of landslides, while in cities like this part, which is correspond to the light area in the coherence map, there are probability of some infrastructure damage. However, there is still a long way to go to verify those analyses. So now I'm working on the SAR amplitude products, and I plan to combine this product with optical images to find more details about the landscape change after the earthquake. And also I need to check and remove some factors that can influence the results, such as the water body and some seasonal factors. So that's all about my GMTSAR project. I really learned a lot during this course. It's already 2 a.m. here. But anyway, thanks so much.
Great, thanks for staying up so late. And that was a nice presentation. Yeah.
Thank you.
And you're going to start a PhD in the fall, it sounds like. That's great. Any questions? I noticed on your damage proxy map, there was a line of damage that seemed to follow. I think it was a river or something in your other image. Have you looked at that feature?
You mean this one?
Yeah, yeah.
Oh yeah, I noticed that, and I checked some map software, and it is a river, but the river actually along the river there are some other other things like the dam and some sand the sand. So I need to check if this is caused by water body, some influence of water body, or it shows the change along the river.
Yeah, interesting. And how was there a lot of shaking, ground shaking in the city area? Shaking of the ground or from the earthquake?
You mean
was there a lot of, did the earthquake cause physical damage to buildings in the city area? Was it a large earthquake?
Yes, it do some damage to it, but this earthquake is not that severe, so the damage is not that severe. But as you see in this region, the earthquakes always occurred. So so we need to check for more information about.
Yeah, it's a pretty, okay, 6.1 is a big earthquake. Okay. Any more questions? Another question, have you tried to use the ALOS 2 data? I know it's hard to get the ALOS 2 data, but it might work better in the mountain areas because it's L-band.
I haven't, but yes, I was advised to test some other data sets.
Yeah, very nice.
Yeah, the earthquake had a known magnitude of 5.8 or something, I think. So it's probably smaller than magnitude 6.
With the L-band data, ALOS, you might be able to look at the other earthquake in 2013. Was ALOS? Oh, maybe ALOS 2 wasn't working in 2013. Huh. Okay. Yeah. And then, of course, the Wenchuan earthquake was huge. So, yeah. Okay, thanks. Very interesting. And thanks for staying up. I don't know if I have all the time zones right, but thanks for staying in there. So, and Matt, thanks for getting your students ready. So I guess we'll move on to Kang, and you've added a student. Great. I think we have plenty of time to do.
Actually, another student in my group just said she wanted to present, but she had some microphone problem, so she asked me to present on behalf of her. So I will do after the first one.
You're going to do the first one?
Maybe the next one, I guess.
Either way, Anwar is one of your students, I guess.
Yes, I'm here.
Okay, do you want to present?
Yes. Well, hello everyone. My name is Anwar. I'm a PG student at University of Grenoble-Alpes in France. And my doctoral research focuses on the glacier dynamics. But first of all, I want to thank all organizers of this event, and a special shout for my instructors, Eric, Lindsay, and Kang Wang. They were super helpful. And also, I want to thank other instructors who were responsive on the slide check. And before jumping into the glaciers, I wanted to test. Sorry, I didn't. Okay, now you can see me. Yes. Before jumping into the glaciers, I wanted to test GMTSAR to retrieve more kind of like a more traditional geophysical signal for INSAR processing, namely subsidence associated with oil and gas production. And I chose the oil field Tengiz, which is located in the western part of Kazakhstan, for several reasons. First of all, I already monitored GPS stations on this oil field. Secondly, this oil field is considered to be the giant oil field with a production rate over 200 million barrels per year. And finally, this oil field is situated in the deserty area with almost no vegetation, which makes like favorable conditions for the INSAR processing. However, you may notice on this map, there is a Caspian Sea to the west, and there are many like ponds. So we may expect some low coherent over these water bodies. This interferogram was made by the Gravy and colleagues using NVSAR and Sentinel images, and they detected the subsidence with a velocity up to 60 millimeters per year. So we also should expect deformation of this level. The processing in the GMTSAR is like the processing of the pair of the images is super straightforward. There are basically two commands to run, but before running, of course, I downloaded the data, the images, and associated orbits. Then I run a popconfig script that makes configuration file, and I used all these default parameters for the Sentinel, except for the threshold snapshot, which is unwrapping filtering, and the recommended one was 0.1, and I used this. And the main script is P2P, and there is a special for the Sentinel, and I use this one. Then I listed the images and the associated orbits, the configuration files. VV stands for the vertical polarization, and 0 is a sequential processing. And voila, I got very nice unwrapped interferogram. And on the bottom left is this signal over the oil field. It's quite small on this on the scale of the interferogram. So, and here is a kind of, if you zoom in, this is fringes of this deformation. So I used the pair of images of March 2020 and March 2022. So for 2 years data. Then I made the map based on the generated GRD file. Yeah, also superposed the GPS station that I used back in the days when I worked in the industry. So I remember we deployed this. I mean, the density of the GPS network is higher in this region because the concentration of the production wells is higher. That's why we deployed a lot of GPS stations here, and we see the subsidence of this region. And here is like fewer stations because there's another oil field which is called Korolovskaya, but is much smaller. And I draw the transit line over these two oil fields, and this is the subsidence I got. So this is over the Tengiz, which is up to 130-ish millimeters, and there is like smaller in the Korolovskaya. So 130. So in the previous study I showed in the first slide was 60 millimeters per year, so which is corresponds to this 2 year like two year data. So, but you may notice this there's a lot of gaps in this profile. Also, if I zoom in this region, so our interferogram is quite patchy. So, and my instructor suggested to fix it using like by 2 ways. So, and first, like obvious way is to decrease the snapshot threshold. So I think I was quite aggressive, and I put 0.02, and the same for the geocode. And another way is, so I could use this snapshot seashell file, but there is another with interpolation that interpolates over the pixels. And I use this to test. Yes, and the run, but now I run only using one subsource, F1. And also further cut this region using this radar coordinates, and it ran super fast, like 5 minutes or so. In the contrast that the previous all the third subsource, I think I ran like overnight. Yeah, that was very nice, like to have the results very fast. Then I ran geocode command, but I got error, so apparently I need also transdat, which is translate from the radar coordinates to the geographical coordinates. And then I got very nice continuous map. So remember, there was a Caspian Sea and transition to the land, and a lot of ponds. I think these things is because of ponds maybe. But over the Tengiz oil field, we have very clear subsidence, and now this vertical profile looks also very nice and continuous. So that's pretty much what I've done. Now I would like to learn to make a time series, and especially for this oil field, so I could see the evolution of this subsidence and maybe associate with a production rate. But the whole reason I took this course, it was to retrieve the horizontal velocity of the glacier flow. And I tried to apply the same methodology that I use for this oil field for the glacier in Antarctica, which is called Astrolab. And I got this interferogram. This low coherent is the ocean, and this part is of the interferogram is a part of the glacier. And I got rather odd results. And my instructors told that it may be because of the SRTM, and indeed, when I checked the SRTM, the quality was quite poor, both for both digital elevation models, SRTM, and the another one is Aster, I think. The both was quite poor, and I couldn't retrieve couldn't retrieve the deformations, but even I'm not positive that this methodology would be appropriate for the glacier processing. Yes, but if you let me to bother you with further with my annoying question, I think I may succeed. And so, but I'm very happy that I learned the basics of the GMTSAR, and I believe it will give me like the big momentum further explore in SAR processing. Yeah, thank you very much.
Great, thanks. Those are some nice examples. Beautiful. Are there any questions or comments about? Oh, here's a comment about there's an 8-meter resolution DEM of Antarctica. Look for REMA. Yeah, that might fix your problem. But my take on this is actually it could be the ice moving, because these interferograms are not usually very sensitive to topography. So you could try a better DEM, but this could actually be ice motion.
Yeah, but SRTM probably doesn't cover this far, right? Because SRTM only covers from positive 60 to negative 60 degrees.
Yeah, there is no data for this latitude.
Yeah, so probably his processing does not have the DEM removed.
I see, but I see. It might not have even been in there. Okay, but still, the ice moves a lot, and so yeah, I wouldn't be surprised if this is real ice motion. But any more questions? The other results, amazing, beautiful data.
Thank you.
Any other questions? I'd be really interested to see the ice results later on, because I think there's a lot of opportunities to use Sentinel data over Antarctica and ice, as long as it's not moving too fast. So sort of a slowish ice streams.
And my comment and maybe wish is maybe to have a like example of a glacier on this download page. Would be nice to follow along, and I think it would be easier to learn.
Yeah, there is one out there. It's called the Lambert Ice Shelf. You can try that one, and you can see floating ice where it cracked and is moving away, and there's some beautiful fringes.
Oh, I didn't know that. Okay, well, I'll definitely look at. Thank you very much for saying.
We don't have any ice examples. We should have many more. The other thing that I see in this interferogram, sorry, I'm taking all this time, but you see the horizontal line at a azimuth of about little less than 3,000. Now, that could be orbit error or something, but it could also be a long track ice motion, because the Sentinel tops mode is sensitive to motion in the along track direction. So you could use the phase shift along those boundaries to actually measure the motion. It's another way of, and that gives you the motion in the horizontal only. So anyways,
Okay.
yeah, it was great.
Thank you very much. Thanks a lot.
More questions? So Osana sent something in the chat, said that she couldn't present the final project, but Kang is going to present that. So take it away, Kang.
Yes, I'm gonna present on behalf of her. So let me put the slide into the full screen. So this is another study of using INSAR to look at the deformation associated with earthquake. And so the earthquake was the earthquake that struck the boundary between border between Afghanistan and Pakistan 3 weeks ago, and it caused a lot of deaths. It caused more than 1,000 deaths, including dozens of deaths in Pakistan as well. So the earthquake caused by the stress buildup from the collision between the India and the Ural area plates. The USGS registered magnitude was about magnitude 5.9, but actually when we did the modeling, it was around 6.1 or even higher. So Akasana made the interferogram using data from both ascending and descending tracks. For the ascending track, that was between June 18th and June 30th, because now we only have one satellite, so the repeat time is 12 days. So the first acquisition was about 9 days after the earthquake, the first post-seismic acquisition. For the descending track, it's shifted by 1 day. So basically, so it's between 20, I think it's June 22 to July 1st. That's what I remember, because I also look at the deformation of this earthquake too. Anyway, so you can read the numbers from the file name. So yeah, for this particular area, the baseline of both tracks is very small. It's for the ascending track, the baseline is 14 meters. For the descending track, it's about 70 meters. That's fairly great for deformation studies. So here's the deformation, the interferograms from the ascending track. As you can see, there are a concentration of fringes around this area, and it's highlighted by this box. The USGS, I think the USGS epicenter was somewhere here, so definitely there was some error in the location. But anyways, for this particular interferogram, you can see there are a lot of fringes that are not associated with the earthquake. Particularly, there is a sharp boundary running across the image. This seems to be a common phenomenon for interferograms in Pakistan and also in Iran. This is generally associated with, we think it's associated with the strong precipitation, and this represents a precipitation front. So, anyways, the interferogram has a lot of noise, and when she unwrapped the interferogram, this to the right is what the Lambert deformation looks like. So if you just look at the pattern of the fringe or Lambert deformation, you think, oh, this seems to be a thrusty one, because there was only one area of deformation for the whole rupture. But later on, if you model the deformation, you see that this is fairly consistent with a strike slip event. So for the descending track, the pattern looks a little bit more complex. So it has From the fringes, you can see there are several concentrations of fringes. And if you unwrap, that's what looks like to the right. So the deformation is characterized by alternating signs of motion in an downside direction. So, and of course, in her exploration, in her experiment, he tried the exercise with different filter wavelengths, and she concluded that for the earthquake, for this particular case, the filter wavelengths does not make a big difference. That's, you know, fairly expected. And yeah, so this is the last slide is the landslide deformation from the descending track. So her hope was to mitigate the atmospheric delay as much as she can and do some modeling. Actually, for this earthquake, I have done some modeling, and the earthquake was fairly consistent with a strike slip event running along a fault that strikes around 210 degrees or so. And interestingly, the earthquake was the concentration of the slip was fairly shallow, but definitely didn't reach to the surface. So there was a very pronounced shallow slip deficit. And I even got the first post-seismic interferogram, that was the data was taken 2 days ago, and the first post-seismic interferogram indicate that there was no early post-seismic slip or after slip that can catch up the shallow slip deficit. I think that's the end of the story for now. Any questions? I hope I explained the slides correctly.
Great, thanks. Thanks for doing the presentation for us, Oksana. Interesting earthquake. So I have a question about the shallow slip deficit, and I don't know if you have a good answer, but it seems like these smaller earthquakes always have a shallow slip deficit. And when is that deficit going to be made up? I mean,
yeah, so that's right. So there was a study that I'm actually also involved in. It's by Ian Klinger's group. And their suggestion is that, yeah, the shallow slip deficit sometimes might be magnitude dependent. So it means that, you know, for the same fault, if it's ruptured by a small earthquake, there might be more pronounced shallow slip deficit. But if somehow it ruptures with a big magnitude, that feature is gone. So, but still mechanically, that's a little bit probably difficult to understand. So I still tend to think that it's probably related to the material property of the fault.
so maybe it's a broad deformation or something. I don't know. Yeah.
Right. That's actually another suggested mechanism.
Okay, well, thanks. Thanks for those contributions, and thanks, Kang, for coaching the students. So we have, I guess we just have one more set from Jawa and Olivia. And again, anybody that wants to present after this, go ahead. We'd like to see things that didn't work. So, but Olivia is first there.
Hi, do you mind sharing the slides for me? So I have limited Zoom connectivity issues.
Do we have the slides here?
Yes.
Yes, it's in the folder.
Okay. Let me get there. Google Drive. There we go. I have to go through all of these hoops to get sign in.
Thank you for doing it.
No problem. Down here. Sorry. In presentations. Slides. Is that the FR?
Yes.
Yeah.
Okay. Oh yeah, I see that. Yeah. So now I can Share slides.
Thank you.
Sure, I'll make it full screen. How do I do that? Slideshow. Perfect. All right.
Perfect. Hello all, my name is Olivia Walbert. I'm a PhD student at the University of Michigan. And today I want to show some preliminary results for using GMTSAR time series processing to better understand tectonic deformation in the FAR triangle. Next slide, please.
Oh, sorry.
Oh, sorry about that. Thank you. So this figure is from the USGS and it illustrates plate boundaries in Eastern Africa as the three limbs that form the FAR triple junction. So these limbs are the Red Sea Rift that bisects the Red Sea, the Aden Ridge bisecting the Gulf of Aden, and the East African Rift, which is this diffuse rift zone that continues through the southern portion of Eastern Africa. These three ridges allow for the divergence of the Nubian plate roughly to the west, the Somalian plate roughly to the north, and the Arabian plate to the east. At the center of the triple junction, shaded in red, is the FAR triangle, which is this geologic depression that is very tectonically active of a region. And it has a long history of volcanism and seismicity, and it's also been the subject of debate regarding the kinematic mechanism that it allows for the accommodation of this three-way divergence. Next slide, please.
Oops. It's coming. There we go. Oh. Try that one. Ah, there we go.
I'm currently working on a project that's focused on making inferences from the seismicity patterns in the FAR triangle. So I created this figure for last week's GMT short course, and this just shows the shaded relief of the region, as well as the focal mechanism catalog that was determined by Kier et al. 2021. I included this figure to reference both the topography and the seismicity in this region and show the variety of faulting mechanisms that are observed that might be useful for interpreting crustal stresses and therefore the deformation in this area. So I decided to focus my INSAR processing project on this region, and the yellow box marks the approximate footprint of the Sentinel-1 acquisitions that I use for the rest of this presentation. The triangle marks a single active GNSS station in this region that I reference for my time series processing. Will you go to the next slide now, please? Thanks. So first, I'm showing a Kml image that was generated during my analysis for unwrapping my interferogram. And I found it really helpful to look at this result and my other results in Google Earth because it helped kind of demonstrate possible influences on my results that might represent sources of noise that I'll need to consider for future processing. So an example I wanted to share is that despite using a landmask to ignore water features, and despite that much of this region is this very arid desert with few expected objects that would result in scattering, there's still some regions of pretty low coherence, particularly in the west, the bottom left of this image. So I was able to use the Google Earth Images layer and found that someone's uploaded images actually show that there are isolated springs that would otherwise be mostly unexpected for this area, and that there is vegetation in these regions where there's low coherence. One last thing that I noticed from looking at this image in this way is that there's some wavy artifacts that are preserved in the interferogram, and they appear to somewhat be aligned with topography. So from the lectures this week, I think that this is evidence that I'm not removing the atmospheric noise sufficiently. So this is another source of noise that I will have to work on further. Okay, and then on the next slide,
let's see, there we go. Takes a minute.
Thank you. So on this slide, I'm showing my DEM on the left-hand side with 200-meter contouring. In the center, I show my unwrapped interferogram with that I've contoured by every pi radians. And then on the right-hand side, I'm showing my line of sight displacements with contours every, I think, 20 millimeters. The line of sight displacement map ranges from about minus 40 millimeters in the northeast to a positive 80 millimeters in the southwest. So it seems that the northeast of the footprint is moving away from the satellite. The center where the color map is, it's kind of this light blue color is mostly stable ground, and the southwest is moving towards the satellite. If you'll go to my next slide, please. I'm showing my time series results, where for these time series results, there's only 3 acquisitions that I'm using, and they only span a period of 3 months. So working through this was useful to be able to learn the general workflow, but these results are rather preliminary. Either way, this plot on the left-hand side shows my velocity map, where the velocity in the northeast is moving away from the satellite at approximately 20 centimeters per year, and the velocity in the southwest is moving towards the satellite at about 50 to 60 centimeters per year. These values seem a bit high, so I think I might have a unit error in here, or I'm not quite sure. The figure in the center shows a plot of my line of sight displacements from my time series, where the individual acquisitions are marked by blue stars, and the average velocity of negative 71 millimeters per year is indicated by the orange line. I had some trouble parsing the GNSS files for the line of sight displacements. So instead, on the right-hand side, I'm just showing you a snippet from the UNR Nevada Reno site that shows for the particular GNSS site that I used the Northeast Z coordinates. So in comparison to their velocities and what I found from the INSAR processing, their velocity is about, or my velocity is about twice as large, but it does seem that relatively the general orientation of motion is consistent. And then I have one more slide, I believe. So finally, this is showing some very preliminary interpretations of these results. So as I mentioned, there are several interesting and diverse models that exist in the literature that attempt to explain how divergence at this triple junction is accommodated within the Far Triangle Depression. One model that I'm showing on the right is from McCluskey et al. 2010, and they're proposing that the Donakiel block, which is this feature near the center of the right-hand image where that dark line cuts through. They're proposing that this is one side of a hinge that is opening. I noticed in my, again, preliminary results that it seems that the velocity map shows that this region that correlates to the position of the Donakiel block has a velocity near 0. So it seems that this might indicate that this region of ground is in fact a static feature. In further comparison to the focal mechanism catalog that shows predominantly normal mechanism seismicity to the west of that Donakiel block, that seismicity, which would probably indicate extension, is correlated with a region that has a high velocity gradient compared to the rest of the image. So I have a final conclusion slide next that just kind of lists the rest of what I foresee that I need to work on. So again, this is rather exploratory, and in the future, I will need to include more data in my time series that spans a greater time span. And I'll need to work on improving the atmospheric correction to beat down some of the noise so that I can better interpret deformation in the far region. And lastly, I just want to say thank you all for this course. I've learned so much, and I welcome any further questions or suggestions or advice to better reveal tectonic signals.
Great, thanks. That was great. I think it's a wonderful start. If there's any questions or comments, I can bring up the chat. Yeah, I think your conclusions are continued work, more data, and hopefully there's more GPS data in the region that you can use to pin down the large scale deformation.
There really isn't, unfortunately. There's been different campaign GNSS stations over the last 2 decades or so, but the single station that I referenced is the only one that seems to have been active in the last 10 years, maybe.
Wow. Yeah, that's going to make it especially challenging, because that large scale trend is you'll have to have 1,000 interferograms to get rid of that, but that's okay. There might be enough Sentinel data to do it. So great, thanks.
Thank you.
You'll need a big computer.
Oh, I'll tell my advisor.
I advise you need and about 50 terabytes of disk space, and then you'll be all set.
Great, thank you.
All right. Oh, I don't have the Google page to see who's next. You have one more student, Jawa, but I don't have the page in front of me.
Yeah, I think it's next will be Elizabeth Hayden from Cornell. Yeah.
Okay. Oh yeah.
Can we see my screen?
Yeah.
Great. So, as Xiao has said, I'm Elizabeth Iden, a PhD student at Cornell, and today I'm going to talk a bit about Santa Maria volcano in Guatemala. This is definitely just a very side project for me. I had some extra data that I was over this region and decided to take a little look. And so this is what the region looks like. There was a large eruption on May 9th, 2014. And I've created 9 interferograms from 8 acquisitions. And just to note, it is pretty highly vegetated here. So you have the whole region. A lot of the interferograms will be more correlated in this more or less vegetated area. But then the actual region of interest here where the volcano is in this smaller box. And this is zoomed in. We have Santa Maria here, and then a lava dome called Santiaguito, which has been there for about the last 100 years, kind of more or less continuously erupting. And so I actually was using some RadarSat-2 data, and Xiaohua was very helpful in actually getting GMTSAR to work with it. So I made a note of the steps that I had to change in order to get it to work. And that included just setting some parameters before actually starting the processing. And then there was one parameter that I had to change during my processing, which was doubling the PRF after step 1 in the processing chain. And after doing all of those things, it worked pretty great. And so I have some interferograms that I can just show where I tried to pick time spans that were surrounding the eruption, looking either after the eruption occurred or kind of co-eruptive interferograms, or even trying to see if there's something before the eruption. And I really tried to make sure there was the smallest perpendicular baseline possible. And so as we can see here, there's a lot of decorrelation, especially right around the region, and that was pretty expected with the amount of vegetation we have, but you can see a bit of deformation here. And so after presenting this yesterday, I think we talked through as a group kind of which way the fringes were going, and then also the order of the dates that I processed the master aligned images in. And it looks like in most of these, we will be able to see some sort of subsidence. So this is kind of right after the eruption to a year after the eruption, where you see this subsidence. And then I just have kind of similar results for other time periods for the data I had. And this one was pretty interesting just because it was covering much more of the volcano in terms of we had more coherence. And so we were thinking that could be some sort of lava flow or maybe a pyroclastic density current that swept through and took out a lot of the vegetation, making it more coherent for this time period. But yeah, I'm just showing a few of the results. I haven't gotten to a point of doing much analysis on this other than being able to get the interferograms going. And then here's just an example of how, even though the perpendicular baseline was very small, there's just a certain point where it's really too long in the time span of 3.5 years was too long to get anything really that's coherent. And yeah, I think that was my last, some more interferograms. And as you can see, there was a lot more coherence in the less vegetated areas to the north. And then this was just one of the interferograms where I wanted to pull out and show the coherence, amplitude, and unfiltered wrapped phase products, just to really be able to see where we had very minimal areas of higher coherence and how they seem to correlate with these more barren regions. But I was just still very happy that we could see anything at the end of the day. But thank you to all the instructors, and especially Xiaohua, who helped a ton with being able to actually get this data processing and working.
Great, thanks. Nice presentation. Challenging area. Are there any questions? I have a couple, but I'll wait to see. Put them in the chat or just want to ask.
Is the dataset2 data in the unfocused raw format, or it's in the SLC format? Because you need to change the PRF. It sounds like it's in the raw format, right?
Yeah, I think so.
They're in SLC actually. The reason that you had to change the PRF is probably due to the changing polarization. Like, even though they recorded the PRF, but if you have a different polarization, like either you have 2 or 4 images coming with the data, then you had to change the PRF accordingly.
So the agency didn't split the data into different polarizations. So they
did. But the PR is just the metadata, not really reflecting the actual acquisition, I guess.
Okay. Because I also processed some dataset data too, but I didn't have to. I guess that's what I'm asking.
Also, they use a pretty strange convention that you need to flip left to right for descending and up down for ascending. I think I don't know why it's that way, but it's just how the data is.
Yeah.
Yeah.
I think the issue is we haven't had much data to process, so none of these came up before.
We basically wrote the code based on 1 pair of data, so that's probably not the best idea when you're developing a software, but you have to live with the fact.
So I have a question. So these were all, this eruption was in 2014. So is that why you chose RadarSat? Because it was the only satellite up there at that time?
Yeah, pretty much. I also, this isn't a focus of my PhD research. It was just some data that my advisor had lying around and no one had processed. No one knew what it was in it. So that was more of the motivation of being able to see what anything was interesting. But yeah, the fact that there isn't really any other data spanning this eruption also made it interesting to look at.
Oh, so that's Matt. Matt Pritchard's probably your advisor, right?
Yes.
Yeah, he does all the volcano modeling and imaging. Yeah, interesting. I suppose you could try, ALOS 2 when, but it's a different time interval. So, yeah, that's great. Are there more questions? There's a couple in the chat. Oh yeah, this is a great question about atmospheric, how to remove the atmosphere. Yeah, and I don't know who wants to answer. I think everyone has sort of a different approach to this. Right. A humid area like that area in the FR is, or even in Southern California in the Imperial Valley in the monsoon summertime, you get huge atmospheric topographic correlated errors. And so I guess what a lot of people do is for each interferogram, they correlate you take a short interval interferogram, maybe just 6 days or 12 days, and you correlate the phase with the topography, assume all the atmospheric error is correlated with topography, and then you remove that as sort of a linear trend. But the problem there is if you're in an area where the fault is right, say on the boundary between low elevation and high, you could remove some real deformation. So it's a problem that, yeah.
You just need to have a lot of data to beat down the noise. That's the ultimate solution. If you have 20 years data, you don't need to worry about these.
Yeah.
Another thing to think about with the atmospheric noise is the timing of the images. So I think it's the ascending is collected at 6 p.m. local time, and the descending is collected at 6 a.m.
Depends
Is that right?
on like where on the globe you're looking at. Certain places have the descending at dawn and others at sunset. In California, it's the other way, that you have descending in the morning and ascending at sunset. It's usually when at sunset the pressure from the sun goes away, and then you have more turbulence in your atmosphere, which makes the quality of the interferogram less as good.
Yeah. Well, shouldn't it be the same local time everywhere on Earth because it's a sun synchronous orbit?
I'm not so sure. I think when
depends on the latitude, I think.
Yeah, that also too.
Yeah. So anyway, yeah, I've definitely seen that difference between sort of the morning interferograms tend to be kind of more stratified, and the evening interferograms tend to be more turbulent. So something to think about. I think ALOS 2 is midnight and noon orbit, so it has different kind of characteristics of atmosphere.
Yeah, I think it's less affected, I guess, in that sense. But the pressure from the sun may give you a stronger atmosphere, I would think.
Yeah, definitely.
All right, well, thanks everyone. Those are great presentations, and of course you've only had a couple of weeks to work on this stuff, so I encourage everyone to keep going and bug us, send us emails about, there are lots of parameters to change and you can't change them all, so you want to consult and see, well, what's the next thing I could do to make better time series or imaging or whatever.
Or even just show off a really nice product.
Yeah,
that'll be good too.
And also, I think there's going to be a questionnaire from UNAVCO about what's good and bad about the course. And really, we need to hear from you, because like I learned a couple things this time that we hadn't really explained what a relative path of an orbit was and how to assemble the data and that kind of thing. So, there are just key things missing, because in our mind, it's obvious, but to you, it's all brand new. So those kind of things will really help for doing it next year. Comments like that. Can we discuss? Okay. Ruby says, can we discuss more in the Slack? Yes. I think that'll last for a year. Okay. Yeah, thank you guys too. Okay. Well, it's 12 o'clock and we're done in a couple hours, and hope to see your research out there someday. Thank all the instructors.
Thanks to everybody for participating.
Yeah.
Nice to have everyone here.
I wish we could go have cookies and go for a pier swim.
Yeah, exactly. The water's warm right now.
I'll go to my bathroom.
It's not really warm. I mean, it's warm for California. It's
yeah.
But we've been getting emails this morning about these juvenile white sharks that are swimming around California. So, but apparently they don't attack people. I don't think. I haven't heard about anything. So, gotta watch. Okay, we'll see everybody.